neuron.
Okay, so what are we talking about today? The nervous system, and specifically how a neuron, a nerve cell, generates an action potential. So first thing we're going to do is construct a motor neuron. So I'm just going to create a motor neuron. We've done this before, so you should be familiar with the anatomy of this cell. This is the cell body where there's a nucleus and other organelles, but I'm not going to draw them right now. Near the cell body, these processes or branches are called dendrites. So that's what I'm drawing now, are dendrites. These processes tend to be a little bit smaller in diameter than this one large process trailing off the end, one end of a neuron called the axon. So I'll just label that axon. This is the cell body or soma. These are dendrites. Dendrites and the cell body are the receiving part of this cell. They receive signals. The axon, as we're going to find out, is the sending end of this cell, sends a signal. So, what does this cell do when it's at rest, when it's not doing anything? Well, what it does is it manufactures chemical called neurotransmitter. Raw material for the chemical, the neurotransmitter, is made up here, created up here, synthesized, and then it's transported down here, where the chemical is actually manufactured, put together, assembled in these axon terminal ends. That's another lecture. So today's lecture is going to focus on how this cell generates and propagates its own action potential. When you hear the word action potential, just think electrical stimulus. So this cell's at rest. I'm going to be another neuron. I'm going to send a signal to this resting cell. In order to do that, my axon, my left arm here, is going to represent my axon. This is my axon terminal. So that's me, a neuron. That's my end down there is going to send a signal to this receiving cell. So my axon terminal has to be somewhere near this cell body because it receives a signal. I can put my axon terminal near these dendrites or very close to this cell body, send it a signal, and cause it to do something. First, we have to examine what this cell environment is when it's at rest. There is something called resting membrane potential that this cell and most cells in the human body exhibit, and that is there is a separation of charge across this membrane, this plasma membrane. In a neuron, we call it the neurolemma. So across this neurolemma, there's a separation of ions caused by something called the sodium-potassium pump, which sits right along the plasma membrane, or neurolemma. I'm not going to go all the way around the cell, but these little buttons that I'm drawing represent something called the sodium-potassium pump, which uses ATP in order to pump sodium ions outside of this cell, while at the same time pumping potassium ions inside the cell. What this does is it creates a charge separation. How? Because sodium is a stronger cation than potassium. Due to the fact that this is a more positively charged ion, we're setting up a situation where the outside of the cell is more positive than the inside of the cell. So we say the net charge of this cell all the way around the cell is positive out, negative in. That's due to sodium ions being outside, potassium ions being inside. This is called a polar situation. Polar means opposite or different on one side than the other. So we have a resting membrane potential. What does potential mean? Potential means the potential to do work. If we separate ions like this all the way around the cell, and create positive out, negative in all the way around the cell. That sets up a potential for this cell to do something. So, now that's this cell at rest, as I've drawn. I'm going to send this cell an electrical stimulus, a neural stimulus. When I do that, I'm going to try to wake this cell up. So I'm going to send this cell a gentle stimulus. When I do that, what happens is this polar situation along the membrane depolarizes. That means if we stretch a rubber band out really hard, we're creating a polar situation and the potential for it to do something, do work. If we gently release the rubber band tension, those two polar ends come closer together. That's like the process of depolarizing a membrane. So we've created tension here by separating charge when the cell's at rest. When I send it a signal, the separation of charge is actually going to get closer together. That's called depolarizing. So this is polar, opposite. When the two charges get closer together, we're depolarizing this membrane. If I stimulate this cell, it will depolarize, the membrane will depolarize right in this area. I stimulate the cell gently, we get mild depolarization in ripples from the point of stimulation. Think of throwing a pebble in a pond. If I throw a small pebble in a still pond, we get little ripples around that pebble entry, and then they die out quickly. Throw a pebble, ripples, and they die out. Same thing here. I stimulate gently, and we get ripples of depolarization that die out fairly quickly from the point of stimulation. Now, if I throw a bigger stone in the pond, we get bigger ripples that go further before they die out. Similarly, if I stimulate this cell with a greater stimulus, we get larger depolarization ripples that go further. What this cell is doing when that happens is called a graded potential. The definition of a graded potential, textbook definition, is a short-lived, localized depolarization based on the strength of the stimulus. So if I stimulate this cell gently, we get gentle ripples of depolarization. If I stimulate it harder or more profoundly, we get greater ripples of depolarization. If I stimulate this cell enough, the depolarization, the graded potential, will cause this cell to reach its threshold point. Threshold is a very important word in this process. If we stimulate this cell enough to reach its threshold, something magical happens. We get a massive depolarization beginning at this point, called the axon hillock. The axon hillock is the anatomical area right here at the beginning of the axon. So let's go back to this depolarization business. If I stimulate this cell, we get a graded potential, ripples of depolarization. What does that mean? What that means is when I stimulate this cell, there are gated ion channels that open up all around the cell. If I send this cell an electrical stimulus, that word depolarization means these two charges getting closer together, and ultimately we will flip these charges like this. What's happening there, realistically, is sodium channels, gates, pores, are opening up all around this membrane. So if I stimulate this cell, sodium channels open up and sodium ions enter the cell. They've originally been pushed out of the cell by the sodium-potassium pump. And if I give it an electrical stimulus, I open up sodium gates. Sodium rushes in. That's the act of depolarizing this cell, because we sent positively charged ions in order to get these two separation charges closer together and to flip. So we're flipping this positive-negative charge all around the cell by allowing sodium ions to rush in. If I stimulate this cell enough to send a ripple large enough of this depolarization activity so that we reach this cell's threshold, when we reach that threshold point, the magic happens right here. A very large sodium gate opens at the axon hillock, and sodium ions that were originally out here, they gush into this cell like a waterfall. That only happens, it's like a light switch. It only happens if we reach this cell's threshold. So to review in about 30 seconds, I stimulate this resting cell. What's happening is we're opening up sodium channels. Sodium ions are rushing in, and it's rippling, having a rippling effect of depolarization around this membrane. If I stimulate this cell strongly enough sodium depolarization will reach this cell's threshold and will open this major sodium channel right here. When that happens, when we flip that switch, we can't turn it off. It's called an all or none response. So, let's say we stimulate the cell, we get a large enough gradient potential to reach the cell's threshold. This sodium gate opens wide at the axon hillock. Sodium ions now rush into this cell with great force and great volume. When that happens, we can't turn it off, and we get a linear propagation. That's what that word means. We get a linear opening of sodium gates all the way down this axon. And sodium ions that were originally out here, they gush into the cell. And it happens in a linear fashion. That means one after the other, in one direction, all the way down the axon. Imagine you have a row of dominoes set up on a table, standing up on a table. If you stimulate the first one, here, give it a graded potential, but you don't stimulate it enough to knock it over. You will stimulate this cell, and then nothing will happen downstream. Now, if I stimulate this first domino enough to knock it over, guess what? I can't stop all the rest of the dominoes from falling over. Similar situation here. If I stimulate this cell enough to open this gate here, I've turned it on, I can't shut it off. All of these sodium gates will open in a linear fashion. This is called massive depolarization, and this activity is an action potential. So that word action potential, that term, 2 words, action potential, what that literally means is massive depolarization all the way down the axon in a linear fashion that we can't shut off. It's all or none. So we've caused this cell to reach threshold, fire an action potential all the way down its axon. Now, how does this cell right itself? How does it get back to normal, to resting potential? Here's what happens after depolarization. Once this gate opens, then this one, then this one, then this one, and sodium's rushing in. As sodium is rushing in to the cell down here, these sodium gates close upstream. After these sodium gates close upstream, remember we have potassium inside the cell. What happens next is potassium gates then open up in a linear fashion. So potassium ions that we have inside of the cell, they start to rush out. So after this sodium business occurs, sodium gates close, then potassium channels open, and potassium ions rush out of the cell. That process is called repolarization. So, always always attach this word with sodium rushing into a cell. So next to depolarization, I'm going to put sodium ions in, and then this word, repolarization, always attach potassium ions leaving the cell or going out. Potassium out. All right, so let's examine a little bit more what this means. Sodium has done its thing. Sodium gates have closed. Potassium gates open. Potassium ions now rush out in such great volume that we reestablish the original polarity of the cell. That's why this is called repolarization. So after these potassium ions rush out of the cell, what repolarizing means is we've reestablished a positive net charge out and a negative net charge in. So we've repolarized the membrane, positive out, negative in, just like the beginning of the story. But we're not back to the beginning, because now we have we have potassium ions outside of the cell, sodium ions now inside of the cell. You might be thinking to yourself, well, if sodium's in and potassium's out, how can we have positive out, negative in? It's because of the relative volume of potassium ions that leave the cell. It's actually greater than the volume of sodium ions that rush into the cell. Anyway, so we've reestablished original polarity, positive out, negative in. But we have a flipping of ions. Potassium's outside now and sodium's inside. What reestablishes the original ion concentration is way back to the beginning of the story, these sodium-potassium pumps. These little pumps are just continuously chugging along, day and night. As we sleep, when we're awake, 24 hours a day. These pumps use ATP that our cells make, and they're just constantly, they're not super powerful. They don't pump an enormous volume of sodium out in a short period of time, but they're constantly running. So at the end of all this business, after repolarization, potassium's out, sodium's in, it's these little pumps that reestablish the original ion concentration of sodium being out and potassium being in. The last of this story is this. This is an electrical stimulus. The flipping of charge across a membrane is not that much different than turning on a light in your house. When you stimulate that light switch, you lift it up, At the point of reaching its threshold, the light goes on, and it's either on or off. So you turn the light switch, you're stimulating it, you're stimulating that neuron. When you reach that neuron's threshold, the point where the light clicks on, electricity flows to that wire, and the light goes on. That's what we've done here. So at the very end of this, we've sent an electrical signal with depolarization all the way down here. Ultimately then what happens is that depolarizing membrane causes that stored chemical neurotransmitter to be released into a space called the synaptic cleft, postsynaptic cell. So this whole business, stimulation, graded potential, threshold, massive depolarization, sending and action potential, all of that, the goal of that is to release chemical from these stored vesicles in the axon terminal. Once chemical is released, neurotransmitter is released, it can bind to another cell and something can happen.